You type a description. A few seconds later, an image appears that looks like it was photographed or painted by a professional. Detailed, coherent, sometimes uncanny. Here's what's strange about how that happens. The model doesn't start by imagining an image. It starts with pure noise, random static, like a television signal with nothing on it. And then it systematically destroys the noise until an image emerges. That process sounds backwards. It is backwards, and understanding it changes everything about how you think about these tools. Let's start with what AI image generators are not doing. They're not searching a database and finding the closest match to your prompt. They're not blending existing images together. There's no hidden image library. The model has no stored collection of cat photographs it retrieves when you ask for a cat. What they're doing is fundamentally different, and honestly, more interesting. The technique behind most modern image generators is called diffusion. And the best way to understand it is to start with how these models are trained, not how they're used. During training, the model is shown millions of real images. But here's the twist. Those images are deliberately destroyed. The training process takes a photograph, say a picture of a golden retriever on a beach, and adds random noise to it in small increments, step by step. After enough steps, the original image is completely gone. What remains is indistinguishable from static. The model's job during training is to learn how to reverse that process. Given a noisy version of an image, predict what it looked like one step earlier, slightly less noisy. Do that well enough across millions of images, and the model learns something remarkable: a statistical understanding of what real images look like, what textures coexist, how light falls, what makes a face look like a face. Think about what that means in practice. The model has implicitly learned that sky tends to appear above ground, that eyes are symmetrical, that shadows fall in a consistent direction relative to a light source. Nobody told it any of that. It figured it out from the pattern of what gets destroyed and what gets preserved across millions of denoising examples. The rules of the visual world are baked in, not as explicit instructions, but as intuitions embedded in billions of parameters. After training, that knowledge is frozen into the model's weights, which means you can now run the process in reverse. Start with pure noise, a completely random image, and ask the model to apply its learned denoising ability step by step until a coherent image emerges. That's image generation, not retrieval, not blending. Learned noise removal applied in reverse. Now, how does your text prompt actually influence what comes out? This is where a second model enters the picture, one called CLIP, developed by OpenAI. CLIP was trained on hundreds of millions of image-text pairs from the internet. It learned to place images and text descriptions in the same mathematical space so that a golden retriever on a beach and an actual photo of a golden retriever on a beach end up close to each other in that space. During image generation, your text prompt gets encoded by CLIP into a numerical representation. That representation then guides the denoising process at every step, steering the model toward images that match your description. It's not understanding what you mean in any deep sense. It's mathematical steering through a very well-calibrated space. Here's the part worth sitting with for a moment. Images are made of pixels, millions of numbers representing color. Text is made of tokens, sequences of words and characters. These are completely different kinds of data. What CLIP achieved is placing both in the same mathematical neighborhood. A sentence and a photo of the thing that sentence describes, they end up near each other in a shared space. That's a genuinely strange and useful thing to have done. This explains something you've probably noticed. Weird prompts produce weird images, but they still look photorealistic. The model can't check whether your prompt makes logical sense. If you ask for a melting clock playing tennis on the moon, it will produce something plausible looking and completely absurd. The realism comes from the model's statistical knowledge of what images look like. The coherence of the concept is your problem, not the model's. There's a reason AI-generated hands have become something of a cultural joke. 6 fingers, melting joints, fingers fused at the base. It's not a bug that got missed in testing. It's a consequence of exactly what learning from images means. Hands are one of the most visually complex, highly variable things in human photography. They appear in every imaginable position, partially obscured, overlapping, in motion. The model's statistical understanding of what a hand looks like has a lot of variance in it, which means its denoising predictions in that region are less certain, and that uncertainty shows up as artifacts. Text embedded in images has the same problem, for the same reason. This matters practically. If a task requires precise detail in complex regions, hands, teeth, embedded text, diffusion models need either extra prompting guidance or post-processing correction. Understanding why the failure happens tells you where to apply the fix. Another thing worth understanding, the seed. Every image generation run starts from a specific pattern of random noise. That starting noise is set by a number called the seed. Use the same prompt and the same seed twice, you get the same image. Change the seed by one digit, you get something completely different. Same text guidance, different starting noise, completely different path through the denoising process, different image. This is why prompt engineering has limits. You can steer the direction, but you can't steer the exact path. The variation comes from the starting noise, which is random. One more piece worth knowing. Most modern image generators don't actually work in pixel space directly. Working pixel by pixel at full resolution would require enormous compute. Instead, they work in what's called latent space, a compressed mathematical representation of the image, typically 8 to 16 times smaller. The denoising happens in that compressed space. Then a separate decoder converts the result back into a full resolution image. This is what latent diffusion means. And it's what makes systems like Stable Diffusion fast enough to run on a laptop. Here's what you're actually looking at when you see an AI-generated image. A coherent picture that was assembled from nothing but noise, step by step, guided by a mathematical representation of your text, using a model that learned what real images look like by studying millions of examples of image destruction. The images can be beautiful. They can also be confidently wrong in specific, predictable ways, because the model is applying statistical reasoning, not visual understanding. There's no concept of what makes sense behind it. There's a very sophisticated model of what images tend to look like. That distinction matters when you use these tools seriously. Prompt engineering, seed control, in-painting to fix hands. These all make more sense once you understand what the model is actually doing. You're not directing a mind, you're steering a denoising process through a space it's learned very well. And the space it's learned is genuinely impressive. If you want to keep building this kind of precise mental model of AI, the one that actually helps you use these tools better, subscribing is how you get the next one. Diffusion. Training by adding noise to images, then learning to reverse it. Clip. The model that connects text descriptions to image features mathematically. Denoising. The core operation, predicting what an image looked like before noise was added. Latent space. A compressed mathematical representation where denoising actually happens. Seed. The starting noise pattern determines which image a prompt produces.